In the last video, we looked at how to represent information about an arbitrary number of accounts using a list, where each account has a number and an account name. At the end of that video, I asked you to write a function that would look up an account number in such a list and produce either the account name if it could find it or produce false if it couldn't. So I hope you've done that, and I hope that gave you some better understanding of what that representation of accounts would be like. Now let me ask you a question. Suppose we have a list like that of accounts, and suppose the list is long, really long. And I don't mean 365 long, maybe I mean 365,000 long, or I'll just call it N for now. The question I want to ask you is, how long does it take to find an account in that list? Well, let's see, if I get lucky and I'm looking for account number 1, then I only have to look at the first account in the list to find it. So that was pretty lucky. If I get a little less lucky and I'm looking for account number 4, then I only have to look at the first 2 accounts in the list to find it. If I get less lucky and I'm looking at, say, account number 14, I've got to look at 5 accounts. If I really get unlucky and I'm looking at account 365, I have to look at all N accounts in the list before I get to 365, because I have to check each of the ones that come before it to see that, oh no, they're not account 365. So on average, if I have sort of average luck, I'm going to have to look at N over 2 of the accounts, because sometimes I'll be lucky and I'll be looking for the first one, and sometimes I'll be unlucky and I'll be looking for the last one, and everything else in the middle will happen. And so on average, I'm going to look at N over 2 of the accounts. So that's not so good. If I have 365,000 accounts, then anytime I look up an account number, I'm going to have to look at half of 365,000. That's not really good enough. It seems like we ought to be able to do better. Well, one idea would be to sort the list by account number, so that account number 1 comes first, and 3, and 4, and 7, and so it's just in increasing order of account number. That would take some work to get it sorted, but it seems like that might be a good idea. The problem is that doesn't help. It doesn't help at all. Not at all. And here's why. The way lists work, remember that with lists we just have first and rest. So the only way we can traverse the list is in order from beginning to end. So whether the list is sorted or not, on average, we're going to have to look at half the accounts in order to find the one we want. So sorting is not going to help. Or actually what I should say is sorting alone isn't going to help. But here's another idea. Let's imagine that we start with a sorted list. And then we'll take the middle of the list. In this case, that's 10y. We'll take the middle of the list and we'll sort of split the list around the middle so that we leave the middle up top like this. On the left-hand side, we're going to put everything that came before the middle. And on the right-hand side, we're going to put everything that came after the middle. And so the important thing here is that in this left-hand list, this one down below on the left, all those have an account number less than the middle, less than 10. And the right-hand lower list, all of those have an account number bigger than 10. And so that's kind of neat. We could do it again. For each of those 2 lists, we could take the middle. So in the left-hand case, it's 3ILK, and in the right-hand case, it's 42ILY. And we'll do the same thing. And we could keep doing that until we get to the point where there's no lists left, where at each level all we have is a single account number and name. And now I'm going to draw these lines in, and this is a thing called a binary search tree. And the important thing about a binary search tree is that at every single what's sometimes called a node, all the accounts in the left subtree of that node have a number less than the root, and all the accounts in the right subtree have a number greater than the root. So everything in this part over here has an account number less than 10. Similarly, everything in this part here, below and to the right of 3ILK, has an account number greater than 3. And this rule here is called an invariant, and it holds true over the entire tree. That's what it means for it to be an invariant. It's true over the entire tree. Now, if I construct a tree like this, we don't quite yet know how we're going to represent it. This is all information. But imagining that this is information, let's think sort of abstractly about how long it would take to find something in such a tree. Well, let's see. Suppose it's going to be the worst possible case. I'm going to look for 14, for example. Well, I look at 10, and 10 isn't 14, so I'm not there. But 14 is greater than 10, so I'm going to completely ignore the left-hand part of the tree. And now I'm going to go down to the right branch of the tree. Let's see, 42 isn't 14, so I'm not there. But 14 is less than 42. So at this point, I'm going to ignore the entire right-hand branch of the tree. And I'll go down the left-hand branch. Let's see, 27 isn't 14, so I'm not there. But 14 is less than 27, so I'll ignore the right-hand branch of the tree. There happens not to be one, so ignoring it doesn't do much, but I'll ignore it. And I go down the left branch. Let's see, 14 is 14, I'm there, I produce OLP. And if I ever get to a branch which has nothing in it, suppose I had been looking for 28, for example, if I'd been looking for 28, then when I got here to 27, I would have tried to go down the right-hand branch, and there's nothing there, and so I would produce false. So how long does it take to find something in that tree? Well, notice that at each step of the process, when we didn't find what we were looking for, we eliminated about half the tree. So each time the tree gets smaller by half. As compared to the list, each time the list got smaller by 1, but here each time the tree gets smaller by half. And so what that means is that in this world, on average, we're going to have to look at log n of the size of the tree, because the tree keeps getting smaller by half each time. And so we're going to find our answer a lot faster in something like this. If, of course, we can find a way to represent it as data. Right now we're talking about an abstract piece of information, and we've done an abstract analysis of how long it would take to find something in it. We'll try to implement it in the next video.